So good afternoon everyone. So it's nice to be a part of this conference being organized at IIT Dharwad on next generation sensors and technologies. So my talk will be about interface electronics for FET based MEMS sensors. It's nice that I'm following this talk with Professor Sina's talk where she discussed about the different types of transistor based MEMS and the device aspects of it. I will be talking mostly about the interface electronics. So before I begin, I would like to acknowledge that the work presented in this talk is work done by many researchers apart from me, including students and my collaborator Professor Sina. So we have seen that MEMS inertial sensors are finding new applications because of the miniaturization and the advent of handheld electronics and IoT devices. A lot of new applications of MEMS sensors have started coming up, and these new applications have essentially fueled new research on how to improve the sensors performance, how to reduce their power consumption, how to integrate them better, etc. So we will see what are the different types of MEMS sensors that were there earlier and what are the new types of sensors that are coming up. So when we talk of MEMS, essentially we mean micro electromechanical systems. So the main component here is the transduction, essentially how the mechanical signal is converted to an electrical signal. So there are different transduction schemes. The common ones are piezoresistive, piezoelectric and capacitive. So when we say piezoresistive, what happens is whenever there is a stress in a film, its resistance changes, which is then detected in a circuit. In piezoelectric, whenever there is a stress, there is a production of some differential charge across two nodes, and that differential charge can then be detected using a circuit. And when we say capacitive, essentially it's some kind of a parallel plate structure in which one of the plates is rigid and the other one is free to move. So whenever the plate which is free to move is displaced, it either changes the distance between the two plates or the effective overlap area, which essentially is change in capacitance, and that can be detected using a circuit. So there are some limitations of this so-called passive transduction schemes. When I say passive, I'm using some abuse of notation, because when I say piezoelectric, it's not quite passive, but piezoresistive and capacitive are truly passive transduction schemes. So one of the difficulties is that CMOS MEMS integration is quite difficult with piezoresistive and piezoelectric, because the materials which are available in CMOS or are compatible with CMOS, they don't have the kind of sensitivities that one would like to have. And when it comes to capacitive, CMOS MEMS integration is relatively easier. However, the size of electrodes required for such capacitive sensors is quite large for a given sensitivity. Then when it comes to front-end electronics, the front-end electronics for some of these sensors is quite complex. When we look at piezoelectric sensors, you need what is known as charge amplifiers, which essentially have very high impedance nodes. Whenever you want to detect a charge, you need to essentially, principle is you dump that charge on a capacitor and then read the voltage out of it. But any capacitor is essentially a high voltage, high impedance node, and high impedance nodes generally are not very good for low noise applications, because they tend to pick up noise from external sources. Similar is the case with capacitive converters for that matter. We use what is known as C to V converters to detect the change in capacitance and convert it to a change in voltage. So in most of the capacitive sensors, one of the things that is of concern is electromagnetic coupling. So it's always capacitive sensors are always sensitive to electromagnetic interference, because they tend to pick up signals, and therefore they use good shielding, and that in turn increases the area of the whole sensor. When it comes to piezoresistive, the kind of interface electronics required is a little simpler, because all that you generally need is a Wheatstone's bridge and some kind of a low noise, low offset amplifier chain to detect the change in resistance. However, the sensitivity of piezoresistive sensors is generally inferior to what you get from capacitive, and it suffers from temperature sensitivity also. So most of the commercial accelerometers we see in the market today are by and large dependent on capacitive type of transduction. So these limitations have led to exploration in so-called active transduction schemes, wherein the MEMS sensor is made up of a transistor. So suspended gate FET based sensors are something which people have been looking at. Essentially, this is a structure in which the gate is free to move over the channel. There is no oxide, but in place of an oxide in a conventional field effect transistor, what you have is an air gap. And then the gate is suspended using some kind of a spring mass system, and it is free to move. So depending on how the device structure is designed, you can have a transistor in which the gate moves along the channel, in which case the effective width of the channel changes, what is shown here. So whenever the gate moves, it changes the effective width, it moves parallel to the plane of the channel, and that change in the width can then be read out using a circuit in which is comprised of this transistor. Or you can also have what is known as vertically movable or out of plane movable, in which the gate can move closer or farther away from the channel, thus effectively changing the air gap. This also changes the characteristics of the transistor, and which can be read out using a circuit which is made up of this transistor. So these suspended gate transistors have some advantages over what is known as the passive transduction schemes. So they have, first of all, they have an easy interface with the readout integrated circuits. The input pair of a differential amplifier themselves form the transistors that the input pair of a differential amplifier itself is the sensor. It could be the sensor transistors, in which case you have a direct conversion from mechanical to electrical inside the amplifier itself. So there are prospects for better SNR, as the amplification first amplification stage is at the sensor itself. So if I can just go back a bit here, if you look at this, most of the conventional passive transduction schemes, how they are done is that the CMOS IC is fabricated separately from the MEMS components, and these are then wire bonded together to connect them up. So this essentially means that the sensor is far from the rest of the integrated circuit, and that has an effect on the signal to noise ratio. So in case of transistor based MEMS, essentially the first level of amplification is much closer to the sensor, which is essentially is likely to result in a better SNR, and it retains most of the advantages of the capacitive sensor. So essentially, if you look at it, this is very similar to a capacitive sensor. It's just like saying that I have a capacitive sensor in which one of the plates of the capacitor is essentially a semiconductor material with source and drain implants. So in principle, it has all the advantages of the capacitive type of sensing, and in addition to that, it has amplification closer to the sensor. And like capacitive sensors, it can be used in a closed loop configuration. So Professor Sina has just talked at length about how these sensors are better than conventional sensors. What we are interested in, how do we go about designing systems and circuits with these sensors? So let's just take a brief detour and see how circuit design is done in conventional CMOS technologies. So if you look at any conventional CMOS, if you see the way the process goes from concept of a given technology to a circuit design in that technology. So first thing that is done is the process design and optimization is done by performing process simulations in TCAD. So once you're satisfied with the process simulation of how the different implants are, what kind of implants are done to control the short channel effects and so on, you do a device simulation to find out the device characteristics. After this, you get the electrical performance of single transistors. Once you get the electrical performance of individual transistors, a compact model is developed. This is an elaborate exercise wherein you try to come up with a set of equations which can be used in simulators to simulate circuits with these transistors. So this compact model is essentially a mathematical model set of equations which describe the electrical characteristics of a transistor for a given width and length. So this good compact model will allow you to choose a wide range of operating points and a wide range of geometries of the transistor to do circuit design with. And then after this compact model is ready, circuit designers then use this compact model to design and optimize circuits using these transistors. And then once the circuit design is done and the layout is done, this design is sent back to the foundry. Since it is done, the design is done on a compact model which has come from the TCAD of device simulation and has been validated with the unit transistors. The circuit performance is guaranteed to match the final outcome of the fabricated device. This is how general CMOS transistor with a very short overview of the entire chain from designing a new technology to designing circuits in the new technology. But if you look at this kind of a route, it is very difficult to use this route for designing circuits with SG-FET type of transistors. One of the reasons is that these SG-FETs, they involve multiple domains of physics. So if you just think of one of any of these SG-FET transistors, you see that the mechanical position of the gate is governed by Newtonian mechanics and the electrostatics forces in the structure. The transistor characteristics depend on the steps used to fabricate the transistor, the semiconductor device physics, essentially the junction depths, the doping concentrations, the resistivities of the materials, etc. All these determine how the transistor actually behaves. And the final sensor output also depends on in which circuit the transistor is used. So how do we simulate this kind of a device? It's not trivial because of these multiple domains of physics that are involved in determining what is the output of a given sensor in any operating conditions. So if you look at a brief, if you just look at some literature on how other groups have done this kind of how the people have tried to simulate these kinds of transistors, one of the things that can be done is you can use multiphysics solvers. So essentially you can take this structure of all the Newtonian mechanics, the electrostatics forces, the transistor device equations and the circuit equations. And then you can all give all of these to a coupled differential equation solver, and the output of that solver can then tell you what is the output of the circuit in the sensor with the sensor. So one of the disadvantages of this is that it is difficult to observe the effects of individual domains in such solvers. Once you get an output, if you want to improve something, it's very difficult to say which part of the sensor should you work on. Should you improve the implants of the transistors? Should you change the operating point of the transistor? Should you change the mechanical structure? It's very difficult to observe effects of individual domains. Further, it is very difficult to capture the transistor fabrication process. So you can define the device using by the implants, depths and so on, but you cannot really simulate the process and then simulate the device that results from that process. So fabrication process steps simulation is not, it's quite difficult to capture it in these kinds of solvers, in addition to the fact that they are computationally very, very intensive, because the kind of equations that are involved are very diverse. You have something which is Newtonian mechanics, which has large time constants, and something which is semiconductor physics, which has very short time constants and involves quantum kind of simulations. So it's quantum mechanical principles. So it's very difficult to, it's very computationally very intensive to solve this kind of systems. The other way people have done it is some groups have tried to construct equivalent lumped circuit models and then simulate the whole thing using a standard circuit simulator. So this has the advantage of being that it can be very fast in simulations. However, these are too approximate, because the kind of these approximations, it is not these may not be sufficient for performance evaluation before fabrication. However, it is very useful for initial exploratory studies. And again, like the previous case, this also cannot capture the transistor fabrication process of these device characteristics. It can only capture the mechanical part and the circuit domain part. There has the transistor component essentially has to be modeled using a conventional transistor, which is a little inaccurate in this case. So other reported works on FET based sensors have mostly focused on sensor fabrication and measurements. There are no reports on how one can perform system design and optimization. This is of course to the best of our knowledge. So one might ask, why don't we just build compact models for these kinds of sensors also? In principle, it is possible to build compact models, but it is quite an involved task. Compact modeling is always a very involved task in terms of man hours required for generating the compact models. And in addition, one has to note that this kind of sensor transistors will be used only in one configuration. It's not like a circuit designer would want to explore a wide range of types of circuits with this, or a wide range of geometries. Typically, one would just use the sensor and play with the rest of the electronics to design the sensors. For example, in any of the standard compact models, if I take the example of 180 nanometer technology, generally the transistors are modeled from lengths of minimum length from 180 nanometer to all the way till like 10 micrometers typically, and similarly for a wide range of widths. So that kind of elaborate compact model is not really required, and it will be in some sense a wasteful effort to try to develop compact models because the use case is not the same as a conventional transistor. So one of the things that we have looked at is how can we simulate this using lookup table based models. So one thing to note here is, though these SGFET devices have multiple domains, the individual domains have well-defined interfaces. So if you look at it, the time constants of different domains are very different. This allows one to independently analyze each domain and integrate a system model using lookup tables. So if you see this, the mechanical structure have a response time generally which are in the order of milliseconds. The transistor process can be simulated separately to give an accurate transistor model for device simulation. The transistor device characteristics change very fast. For example, the channel formation and the quasi-static model is good enough for these kinds of things, and these are all phenomena which happen in hundreds of picoseconds. For example, once you bias a gate, the channel formation and the change in the channel due to change in the gate is generally in the order of hundreds of picoseconds. It's only when you look at very, very high speed circuits that one looks at non-quasi-static effects and complex models. But for these kinds of circuits wherein the operating frequency is quite low, one can actually discretize the gate and for each position and simulate the transistors separately for that position. For example, if you have a gate which is moving, you can actually analyze the transistor for each position of the gate and then collectively find the output current change in the current due to this kind of motion. So essentially the transistor characteristics are change very fast, whereas the mechanical transistors mechanical characteristics are quite slow. So the readout circuits can be simulated with sensor transistor and MEMS LUT models for system optimization. So the device LUT models can include capacitance variations, making the overall circuit simulation pretty accurate. So if you see how one would go about doing this is, you can do the electromechanical simulation of the suspended gate MEMS structure using a conventional MEMS simulator, like one of the examples is Cointerware. Once you do the MEMS simulation and you are satisfied with the, let us say, the frequency response of the moving structures, the sensitivity, when I say sensitivity, it's the acceleration to displacement sensitivity of the MEMS structure itself. Then what we can do is we can take this various range of gate positions or the different displacements and simulate the transistor for each of these displacements. So for example, if I have a vertically movable gate and the gate moves from a height of between an air gap of 100 nanometers and 200 nanometers, I can actually take individual points like 100 nanometers, 105 nanometers, 110 nanometers and do a device simulation for each of these gate positions, and I will get a transistor characteristics for each of these gate positions. These mechanical parameters and the electrical parameters for each gate position can then be saved in the form of lookup tables, and these lookup tables can then be simulated in essentially in a circuit using Verilog models. So in the final simulation what happens is, what you have is a set of lookup tables which predict the device, the sensor behavior for each input of acceleration, and this can then be used in a overall circuit simulator to find out what would be the output of a sensor circuit. So let us take an example of how circuit design can be done with this technique. So let's say we have to design an in-plane movable gate sensor. So this is an example of how such a device would look like. So you have a proof mass which is suspended by folded beams, and below the proof mass is embedded the gate of the transistor. This gate is now suspended over the channel. So you see that there is an air gap between the gate and the channel, and the channel is formed in the substrate which has the source and the drain. So what happens is, whenever there is a mechanical displacement, this gate will move along this axis, and that will result in a change in the transistor characteristics. Let's say if we have to design this kind of sensor, how do we go about designing in the various steps? So the first thing would be to do the mechanical analysis. So you can define this mechanical structure as shown here in let's say Coventor MEMS Plus or any other MEMS simulator. You optimize the design of the mechanical structure, the size of the weight of the proof mass, the dimensions of the beams, etc., and do a simulation to find out the mechanical characteristics, which is essentially you look at the cross axis sensitivity, the prime axis sensitivity, and the displacement versus frequency. So once you are satisfied with the mechanical structure's performance, the data for the different gate positions for different values of acceleration can be saved as a table for interfacing with other domain analysis. So you take this data and keep it aside. So that is step number 1. Then you can take the different gate positions which are predicted by the MEMS simulation. So for example, if you are looking at an acceleration range of plus minus 5g, you know that the gate positions will be over a certain range of values for this particular acceleration. So in this case, it is in the order of plus minus 5 micrometers for an acceleration of plus minus 5g. So for this range of values of gate displacements, for each of these values, you can now do a TCAD simulation to find out the electrical behavior of the transistor. So before you do this, you can of course do a process simulation to find out the actual junction depths and for a given process. I am not talking about it here because that is something which we have done and presented at a submitted to a conference. It's going to be presented towards the end of this month in IEEE Inertial. But nevertheless, even if you don't do a process simulation, even if you do just the device simulation, you can just predict the current through the transistors for the given gate positions that you have. And if you want final simulation, of course the process simulation will help you get more accurate results in terms of what is the output current for a given gate position. And the MEMS structural layer need not be included in this simulation because you are just looking at each individual gate position and you are not looking at the mechanical motion in this aspect. So then for this, once you do this simulation, you will get a set of characteristic curves. In the case of a transistor, what you have is input characteristics and output characteristics. So which will give you the ID versus VG and ID versus VD. You will get different set of characteristics for different gate positions. So for example, here as you increase the width of the channel, the ID VD will change, and the increasing width is because of the change in the gate position due to acceleration. So now this IV and CV data, it can be stored as lookup tables, which will be used in the overall system simulation later. Now once you have the mechanical and electrical data in the form of tables, what you can do is you can do an overall simulation in Spectre using Verilog A. So the acceleration signal to the sensor is modeled as a voltage. It is connected to the MEMS, it is interfaced with the MEMS lookup table. So what the MEMS lookup table does is it looks at the value of acceleration and outputs you essentially read out what is the gate position for that input acceleration. That gate position in Spectre is again modeled as a voltage. Mind you that this voltage means nothing in terms of electrical quantities, but in the simulator we just use it as a node voltage. That node voltage is connected to the second module which has the lookup table for the transistor characteristics. Now once you get this gate position, which is represented as a voltage, you can read out the transistor characteristics for that particular gate position, and that transistor characteristics is then interfaced with the rest of the CMOS electronics to predict what is the output of the sensor. Similarly, you can also include the transistor capacitances to have a more accurate simulation of the overall sensor. So, for example, we have done this kind of methodology to design a circuit with a in-plane movable suspended gate transistor. So we have the acceleration input which goes to the MEMS LUT, that goes to a lookup table which has the transistor characteristics. Now this entire thing can now be used in a differential amplifier as shown here. So you have you can explore all the kinds of things, whether you want to use resistive load. In this case we used a current source load with common mode feedback with a fully differential configuration from input to output. So this allows you to actually do a simulation in which you can apply an acceleration which goes through the mechanical part, that goes through the transistor. It then comes out as a output voltage, which can then be used to simulate different kinds of circuits. So to illustrate here, this is what we have seen. So here in this case, we did a DC simulation for DC inputs of acceleration between 0 and 5G. You can actually plot the drain current, the drain voltage, and even look at what is the effective width at each of these acceleration inputs, and you can do transient simulations which will actually be able to predict the output voltage from the sensor circuit, and then do your design optimizations and go ahead and design your whole systems. So this doesn't stop here. There are a lot of design choices for sensor interface circuits for achieving high performance. You can use lock-in amplification, you can use chopper stabilized amplifiers, you can have closed loop operation. So depending on what kind of sensitivity and what kind of performance you're looking at, you have various design choices at the circuit level. This design technique opens up this entire types of circuits and allows you to analyze and simulate and evaluate these different types of circuits and try to design systems which are more confidently. So let's see, for example, one of the things that you can do with accelerometer sensors is put it in closed loop. So this is the same structure which I had shown earlier, wherein you have this folded beam kind of structure with the proof mass and the gate under the proof mass. You can put it in a closed loop by using a comb actuator. So essentially, whenever there is an acceleration, the gate moves in one direction, and you can detect that motion in circuits and then construct a closed loop feedback through actuators to generate actuation voltages to these actuator combs, which will bring the gate back to the original position. This will essentially bring all the advantages of closed loop systems over open loop systems to these kinds of sensors. So you can even design and simulate these kinds of sensors and evaluate the performance. So this is something that we have done using a differential amplifier for the IPSG FET. You can connect the output of this. This is essentially the same circuit which we have shown earlier, using the suspended gate transistors as lookup tables and MEMS as lookup tables to predict what is the output voltage. This output voltage can then be given to any controller depending on what kind of feedback system, proportional plus integral, whatever the kind of thing you want to explore. The output voltage of the controller can be given to a charge pump and an actuator, which will then bring the gate back to its original position. So this actuator, mind you, is again a micro electromechanical system. So it has electrostatic forces and mechanical forces which will determine what is its actual operation. So the same procedure we have used for transistor thing can be used for the actuator. So essentially you can construct a lookup table for the actual position of the actuator for different actuation voltages. Use that as a lookup table to close this loop and do an entire loop simulation. So circuits as sophisticated as this, wherein you have the acceleration input going to a MEMS lookup table, which determines the width of the transistor, that essentially tells you what is the transistor characteristics, that goes to a amplifier, then to in this case we have shown how you can interface it with a integral control. So you have an integrator, which is essentially a transistor op-amp, in this case transconductance based integrator, to a charge pump and an actuator. So this kind of sophisticated systems with elaborate circuits and MEMS can be simulated, and you can actually get predict the overall performance and be confident of your designs before actually fabricating and testing your designs. So essentially we have seen how lookup table methods can be used quite efficiently for analyzing FET based sensor systems. While this is quite exciting and interesting, there are some limitations. We have shown that we can do DC and transient simulations. However, one of the things that we are yet to do is how to do AC simulation. It is possible in principle, but it requires development of small signal models, and these are essentially required when designing closed loop systems to check for stability and so on. The other very important thing is how to do noise simulation, because one of the very important factors of any sensor development is to be able to predict its signal to noise ratio while the design stages itself. So incorporating noise analysis into this framework is something which needs to be investigated and done. And of course, one needs to validate these models with actual measurements. So with that, I'll close my talk, and if there are any questions, I'll be happy to take them. Yeah, thanks a lot.